Welcome to this explainer. Today we're taking what usually looks like just another intimidating academic syllabus, and we're going to transform it into your absolute ultimate blueprint for a career in technology.
So let's jump right in. We got to ask the big question that practically every single computer science student wonders on day one. What is the actual mathematical foundation of artificial intelligence and cryptography? Well, the answer is discrete structures. And trust me, it is definitely not just arbitrary math. This is the foundational course that builds those crucial analytical and problem-solving skills you absolutely have to have for algorithm design, network analysis, cryptography, software engineering, the whole shebang. It is literally the secret sauce of computer science. Today, we're breaking down this 125-point course syllabus into 5 main areas: the secret language of computing, logic, sets, and AI, navigating networks and graphs, cryptography and combinatorics, and finally, your blueprint for success. Section 1, the secret language of computing. Building straight off your engineering math 1 and 2 prerequisites, your calculus and linear algebra, this course acts as a really critical bridge. It introduces a completely new way of thinking that's required to actually prepare you for solving complex real-world software problems. What's super interesting here is the specific inclusion of Performance Indicator 6.3.2. It asks learners to understand the relationship between the technical, socioeconomic, and environmental dimensions of sustainability. It's a great reminder that applying these math principles isn't just about cranking out efficient code. It's about using logic to responsibly solve real societal needs. Section 2, Logic, Sets, and AI. All right. Covering modules 1 and 2, we hit the core concepts of set theory and propositional logic. We're talking Venn diagrams, power sets, truth tables, predicates, quantifiers, and the principle of inclusion and exclusion. Now, I know some of that might sound familiar from high school math, but believe me, the application here is on an entirely different level. Because the crucial takeaway is that you aren't just memorizing formulas here. You're going to actively use these logical operations and power sets in massive real-world applications. Think database systems, data mining, digital circuit design. Even more importantly, this is the exact mathematical logic you need to construct actual artificial intelligence frameworks, expert systems, and formal software testing. It's huge. Moving on to Section 3, Navigating Networks and Graphs. Modules 3 and 4 introduce some pretty complex relational mathematics. We're looking at relations, posits, lattices, and specific function types like injective, surjective, and bijective functions, plus Wursall's algorithm. Honestly, it helps to just think of these concepts as the structural wiring for our entire modern digital world. Just consider the real-world difference between these two key graph theory concepts. On one hand, you have Euler paths, which have real-life applications in network routing, basically helping efficiently route all that internet traffic. But then on the other hand, Hamiltonian paths are what assist in path planning, navigation, and decision-making in robotics. It's absolutely fascinating how these different mathematical paths solve completely different engineering problems. And when we get into the advanced applications, things get even more exciting. Knowing how to manipulate posets and lattices, that directly translates to building those massive recommendation systems you interact with every single day on social media networks. It's the core logic behind task scheduling, database query optimization, and designing robust information flow and security models. Now, surprisingly, the syllabus doesn't just stop at technical execution. It explicitly maps these lattice and function concepts right back to engineering ethics. Performance Indicator 7.1.1 actually asks students to identify situations of unethical professional conduct and propose ethical alternatives. The ultimate goal is to make sure we're designing secure, ethical models for data dependency rather than just functional ones. Section 4, Cryptography and Combinatorics. Okay, this is what I like to call the heavy machinery of the course. Here, we graduate to advanced algebraic structures with one binary operation. So think groups and monoids. Alongside that, you'll tackle the pigeonhole principle, permutations, combinations, and recurrence relations. Make no mistake, this is serious, high-level combinatorial problem solving. But why does all that matter? Well, consider the real-world applications. By mastering things like cyclic groups and generating functions, you are actually learning the exact mathematical language required for cryptography and network security. This is the math behind error detection and correction, automata theory, and ensuring maximum algorithm efficiency. You're literally learning how to make the internet secure. Finally, Section 5, Your Blueprint for Success. So, the continuous assessment breakdown is highly structured. You've got the theory component with MCQs, class tests, and open book exams for 20 marks. Then the tutorial component brings numerical assignments for 25 marks, plus a 30-mark mid-semester exam. It definitely demands active participation, but the payoff is huge. It rewards you with a potential 75 marks before the final exam even begins.
Out of the 125 total course marks, a massive 75 marks come entirely from in-semester assessment. That leaves just 50 marks for the end semester examination. So your consistent day-to-day engagement during the semester carries way more weight than just trying to cram for a final exam at the last minute.
And A, if you want to dive deeper outside of class, the syllabus highly recommends some great external self-learning resources. Specifically, it highlights 3 NPTL courses provided by IIT Robar, IIT Madras, and IIT Bangalore. These are fantastic high-level resources to really reinforce everything you're picking up from the core modules. So there we have it. We've walked through the entire syllabus, from basic set theory all the way up to advanced cryptography. You now hold the exact mathematical blueprint to algorithm design, artificial intelligence, and secure networking. The only question left is, how will you use these discrete mathematical tools to build the future? Thanks for joining me on this explainer, and I really can't wait to see what you create.